Hey folks, for this screencast, I'm going to make a rocket simulator. I'm teaching spacecraft design this semester again, and just like last year where I made a simulation in MATLAB where I simulated a spacecraft going into orbit, this time I'm going to make a rocket go into orbit, and so eventually I'm going to make a two-stage rocket simulation. Now, I already have a program called ksp2d.py. It's already in my GitHub, my Python GitHub in Astrodynamics in the KSP folder. This code is very, very long and kind of hard to go through. I didn't want to make a video where I just went through the code and kind of just explained it. So I was just going to build the code from scratch, and I was going to do it the same way I did my seminar series last year, where I build everything up one at a time. Okay, so the first thing that I'm going to do is I'm going to make just a projectile flat Earth model. So you can see the path. So it's in my Python GitHub Astrodynamics Rocket Seminar Series, and the function will be called projectile flat Earth. So the first thing that we need to do is build a dynamic model. And in order to build a dynamic model, we need to have differential equations. And then once you have those differential equations, you need to then integrate those differential equations numerically, which means you need the integration toolbox from SciPy. So pretty much every code I make has to have NumPy, the numeric. Why is it giving me an error already? Oh, it's unused. I'm using Spider 4 here. I've been using this in class the last couple weeks, and so it looks like it has auto completion and stuff, which is kind of cool. So I figured I'd give it a go. All right, so what we're going to do is we're going to make a routine called derivatives. And basically this is going to be where we pass it our state vector and then our time. For right now, our state vector is just going to be two variables. So I guess, what should I do? I think I should heavily comment this, right? Because you guys are going to watch this YouTube video, sure, but then you're also going to download the code, and maybe you don't want to watch my video. So here's where we import all the modules we need. So this is, numeric Python, and then this is, MATLAB style plotting. And then, of course, I already forgot, import SciPy dot integrate as Sci. And this is the integration toolbox, okay? Then here, this is going to be our equations of motion. This is like F equals ma. This is our differential equation. We basically need to tell the computer or the software here what the derivatives are. A is also mass times the second derivative of altitude. And I'm going to assume that the center of the Earth is for now I'm actually doing a flat Earth model. So the z-coordinate in this case is just the altitude above the surface. Okay, we'll probably change that later in a subsequent video, but for now the z-coordinate will just be so z is the altitude above the surface of a flat Earth, and this is in meters, and then z dot is the velocity, and then z double dot is the acceleration. Okay, so we have a second order, so I'm going to put second order differential equation. And the reason why we have a second order differential equation is because we have F equals mass times z double dot. Okay, so in order to have a integrated second order differential equation, the state vector, so state vector for now is going to have two states. So z is going to be the first row of that array, and then I'm going to put velocity z is the state vector in the velocity z is the second row of that state vector. Okay, so then we need to compute the state dot vector. Okay, so I'm just going to go ahead and write this in, and then we'll fill in the code later. So state dot is, I'm going to create an array, np, I like as array. I've looked this up, the difference between array and as array, and I've always used as array. I think there's a subtle difference, but I don't necessarily think it's a big deal. Let me turn off notifications on my phone so I don't get distracted. So anyway, so if you look at the state vector, the first row is z, So the derivative is z dot. The second row is velocity z. So that means the derivative of velocity is the acceleration. And so I'm going to call that z double dot, z dd dot. Now I could put in here, you know, obviously z dot is velocity, but I might do some things later. So I just kind of want to leave it this general here. Okay, so then let's compute z dot. Well, z dot is just the velocity, right? The derivative of position is velocity. Okay, so that one's easy. So this is what's called the kinematic relationship. Okay. Then we get into the, you know, compute acceleration. And I already kind of alluded to that here. We're going to use Newton's second law, and that's going to say that z dd dot is just the, you know, the forces divided by the mass. Okay, so then there's a couple things that's happening here. Well, first of all, we need to compute the total forces, okay? And I'm going to write a couple things down, right? I'm not going to code all of these, but I'm just going to write them down. We have gravity. We have aerodynamics. We have thrust. Okay, all of those things are going to put force on the system. And so for now, I'm going to say gravity is just 9.81, because that's the surface gravity, times mass. And then the aerodynamics, I'm just going to say is 0, because I don't want to deal with it right now. And the thrust is 0. So then the total forces is just gravity plus aero plus thrust. Now here's the thing. One thing I forgot to do is that z is positive up, which means gravity needs to be negative. So we're going to add that in there. Okay? This function also needs to return state dot. Okay? That's how this definition is going to work. The definition is going to pull out the states, compute the first derivative of z, then it's going to compute the gravity force, the aerodynamic force, the thrust force, add them all together, compute the acceleration, create this array, and then return it. Okay, that's all this function is going to do. All right? Now, one thing that you might have noticed is that we have this mass term here. So what I'm going to do is I'm going to create a global variable called mass. And I'm going to say these are my globals. And then what I'm going to do is I'm going to define some constant parameters up here. Okay? So the first one I'm going to do is I'm going to define my rocket parameters, right? So the mass of my rocket, I'm going to assume that I'm building like a hobbyist rocket. So I'm going to say that it's only 640 grams. So that's mass in kilograms, okay? And that seems pretty good. Now this function on its own, I'm going to zoom out for a second so you can kind of see what's going on. This function on its own won't do anything. We have our importing toolboxes, then we have some constants, and then we have the derivatives routine, but it won't do anything unless we integrate these equations of motion. So I'm going to put, you know, everything below here is the main script. Okay, so I'm gonna basically define some methods above, but I'm gonna kind of make the main script below here. So the first thing that we have to do is figure out what our time window is. So I'm going to assume that the rocket is going to stay in the air for 30 seconds, okay? So I'm going to say the initial time is 0, the final time is 30, and then give me 1,000 data points, okay? That's the line space, or the lin space command. Okay, and then what I need to do is I need to go ahead and simulate. So I need to say that my state out is psi.odint, so that's the ordinary differential equation toolbox. And then you'll see it actually tells me exactly what my functions are, or my input arguments are. So the first one is the name of the function from above, so that's derivatives. The second one is the initial conditions. I haven't created this variable yet, but I'm just going to call it state initial. And the last one is the time, which I just defined above. Okay, so let's make some initial conditions then. So initial conditions, what does that mean? Well, for every differential equation, you basically need like boundary conditions, just like when you're doing like partial differential equations of like heating a pipe. You have boundary conditions that propagate the system forward. So in a time domain differential equation, you don't have boundary conditions, you have initial conditions, which basically just says, what is the rocket doing at t equals 0? At t equals 0, I'm going to assume that the rocket is on the ground, it's on the surface of the Earth. And again, remember, this is a flat Earth model, so I'm assuming that z starts at the surface of the Earth. And I'm going to assume that the velocity of the rocket is 164 meters per second. So this is meters per second, and this is in meters. Okay, and that's upwards, right? So hopefully the rocket will kind of do this parabolic trajectory. And then basically I put this into an array, and I say, all right, give me the array z0 and vel z0, and I'm going to go ahead and change this variable to vel z. Okay. Now at this point, the function should run. So let's just go ahead and run it, see if we get any errors. Let's go to the variable explorer, and it looks like I have a state out with 1,000 rows and 2 columns. So that's good. The reason why it's 1,000 rows is because the time vector is 1,000 rows, and then the number of columns is 2, because remember I told you that we have a second order differential equations, which means we have 2 states. Okay, so there's our time window. This is our numerical integration call, and then we're going to rename some variables. So I'm going to say that z out, basically the output of the numerical integration scheme, is state out all comma 0, and then I'm going to say vel z out is state out of all comma 1, and then I'm going to plot. Okay, so I'm going to plot the altitude first. So plt dot plot t out comma z out, plt dot x label, that's time in seconds, throw in a y label, and that is altitude in meters, and then plt dot grid, and then I think that's it. Do I need a show in Spider? I do not need a show in Spider. All right, so there's my altitude. So it looks like I didn't simulate long enough, right? So it shot up in the air, it hit apogee and came back down. But it didn't hit the ground. So let's simulate a little bit longer, say 40 seconds, and try that again. And it looks like that was too long. So let's try, say, 35. And hopefully that seems like it's good enough. So it hits the ground at around 33 seconds. Okay, let's plot the so first this is altitude, and then the next one is velocity. Okay, so I'm just going to copy this, right? So I'm going to grab this guy, Alt W. Oh, that did not work. Looks like my key bindings are not correct. So that's Control C, Control V. I'm going to change this to vel z out, and then I'm going to change this to vertical speed, right? Or it's basically it's more like normal speed. Eventually, we're going to do a planetary model, so this is going to be like normal speed. Sure. Okay. You know what I forgot to do is I forgot to say, hey, put this on a new figure. So I should have 2 figures now, and I do. Okay, so this looks pretty normal, right? My velocity is linear, and it's because my acceleration is constant, right? So my velocity is initially positive. It goes down to 0. That's where I hit apogee. So right at around 16.5 seconds, which is right here. At apogee, I hit apogee, and then I come back down. Okay, so there is my projectile flat Earth model. Okay, so in the interest of not making these videos too long, I'm going to go ahead and stop there. And the next thing I'm going to do is, I guess, make the gravity model a little bit more realistic. Okay, so I hope to see you in the next video, and I hope you enjoyed this one.